Autotransformer, which is also called as variac or dimmer stat, which is used to obtain the required voltage from the available voltage. That is, it can be used to get the step up voltage or it can be used to get the step down voltage. And if you come to the single phase transformer, or also called as two winding transformer, is used to obtain the step down voltage or step up voltage. And if you notice, from auto transformer and single phase transformer, the same requirement can be met by these two. That is, we can obtain step up voltage or step down voltage. So if we are obtaining the same requirement from these two, then there will be some conditions that will make us to prefer auto transformer or single phase transformer. Now let's know them. A single phase transformer or two winding transformer consists of a core on which there will be insulation present and on which winding is wound, and the side of transformer at which source is connected is called primary side of transformer, and that winding is called primary winding, and the side of transformer at which load can be connected is called secondary side of the transformer, and that winding is called secondary winding of transformer. And if you notice that here there will be electrical energy, and because of insulation there is no conducting path for the current, and here this electrical energy is converted into magnetic energy in the core, and then that magnetic energy is again converted into electrical energy. Means here there is no electrical connection between primary winding and secondary winding, which means here there is electrical isolation, in which electrical energy from one circuit is transferred to the secondary circuit with magnetic coupling. There is no direct connection between primary winding and secondary winding. And coming to auto transformer, which consists of a rectangular strip type core which is drawn radially, and on which there will be insulation, and on which winding is wound like this, and the other end of the winding is brought out like this. Let these two ends be A and B, and output energy is collected through a moving contact which can be moved over these turns to get the required voltage from the available input voltage. And this you can understand from the schematic diagram. Let us suppose this be the A end of this winding, and this be the other end of the winding, and this moving contact is this, which can be moved over these number of turns to get the required voltage from the available input voltage, which is given to the load. So if input source is connected like this, then the required output voltage from the auto transformer is collected like this. This is load, and which gets the required voltage by moving this moving contact over these turns of the auto transformer. If suppose the applied input voltage is 400 volts AC, then if the moving contact is at this position, let the load is receiving a voltage of 300 volts. Now to get 200 volts, then we must move the moving contact to a position corresponding to the 200 volts point. And if the load requires 100 volts, then we must make this moving contact to move over these turns to the corresponding point at which 100 volts is available. So from this you must understand that auto transformer is used to obtain required voltage from the available input voltage. And the other important point is it consists of single winding, whereas single phase transformer consists of two windings. And we discussed that the side of transformer at which source is applied is called primary winding side, and the side of transformer at which load can be connected is called secondary side of transformer. And if you notice that in single phase winding, the primary winding and secondary winding are electrically isolated. And whereas in case of autotransformer, there is no electrical isolation between primary winding and secondary winding. And now you might get a doubt in case of autotransformer that what is primary winding and what is secondary winding. Let us suppose the moving contact is at this position, then this total winding comes under primary winding, and from this point to the neutral point, this portion of winding comes under secondary winding. But if you notice that here, this portion of winding is common to the primary side and secondary side. So this portion of winding is called common winding. So the third important point here is that a portion of winding is common to primary and secondary, which is called common winding. And the fourth important point is here, there is no electrical isolation between primary winding and secondary winding. And the fifth important point is that if you observe in single phase transformer, the secondary winding is receiving power from the primary winding through induction process, because there is no electrical connection between primary winding and secondary winding. But if you observe from the autotransformer that load receives some power directly from the input source and some power through induction process. Therefore, in case of autotransformer, load receives power conductively and inductively also. So here the fifth point is, in autotransformer, load receives power through conduction and induction process. Therefore, the applications of autotransformer are, it can be used as booster in distribution system in case of voltage drop. That is, to compensate the voltage drop in distribution network, autotransformer can be used as booster. And the second important point is, it is used to start motors, because few motors can't be started directly by applying the input voltage. And in interconnected systems, autotransformers are used to change the voltage levels. And the fourth application is, it is used as variac, that is to get the required voltage from the available input voltage. These are the important applications of autotransformer. Now let us suppose that input voltage is applied, and let that be VH, and let the output voltage be VL, and input current be IH, and output current be IL, and primary number of turns be NP. The number of primary turns represents the turns from A to B, and here the secondary number of turns means the turns which are common to both primary and secondary side. So here the number of turns common to both primary and secondary side is the turns present between C and B, that is the turns present between the moving contact and B. So let those be NS. Therefore, the turns present between A and C represents NP minus NS. And now this is the important point that you must keep in mind, that transformation ratio K is taken as the ratio of low voltage to the high voltage. Whereas in case of single phase transformer, K is taken as the ratio of secondary voltage by primary voltage. But in case of auto transformer, please remember K as VL by VH, because by remembering K like this, it will make us simple to recall the formulas relating to auto transformer. So that is equated to IH by IL. Here IH represents the current on high voltage side and IL represents the current on low voltage side, and which is equated to NL by NH. As power is taken as constant in transformer, so if VL into IL is constant, then if voltage is high, then current will be low, or if current is high, voltage will be low. And if you observe this diagram, the output power is VL into IL. So let us represent that with S out, which is equal to VL into IL. And if you recall the concept of single phase transformer, that the primary current and secondary current are in phase opposition. So the primary current here is IH and secondary current means the current flowing in the common winding. So if this direction is like this, then because of phase opposition, the common current direction will be like this. Let that be IC. Now you can take IL is equal to IH plus IC. So VL into IL is equal to IH plus IC. So VL into IH plus VL into IC. And it is discussed that the load in auto transformer will take some part of the power directly from the input supply, and that is through conduction process, and some part of power through the induction process. If you observe that VL into IH, so this is the a part of output power and IH represents the conduction current. So VL into IH represents the conduction power, and here let's represent that with SC, and VL into IC. IC is the current flowing in common winding, and load is receiving this current through induction process. So VL into IC represents the induction power. Let that be SI. So of total output power, some part of power is through conduction process and some part of power is through induction process. Therefore SI is equal to S out minus SC, and S out means VL into IL and SC means VL into IH. Take VL common, so IL minus IH, and now take IL common, so 1 minus IH by IL, and IH by IL we took K, and VL into IL represents the output power. Therefore inductive power SI is equal to output power into 1 minus K. So that implies SI is equal to S out minus K into S out, and S out is the output power received by load, and we discussed that load will receive a part of power directly from the input supply, and that we called it as conductive power, and some part of power through induction process, and that we call it as inductive power. And if you observe that inductive power is equal to output power minus K times S out, means this will represent the conductive power. Therefore SC is equal to, that is conductive power is equal to K times S out. These are the two important relations. And now let's compare auto transformer and two winding transformer, and we took the transformation ratio constant is equal to low voltage by high voltage, and few others will define K as VH by VL. That is different case, but remembering K like this will make us to recall the relations between auto transformer and two winding transformer simple. And here we define K is equal to VL by VH, so which will be less than 1. Therefore 1 minus K will be less than 1, and 1 by 1 minus K will be greater than 1. Now remember this. And now comparing the kVA rating of auto transformer and two winding transformer, and we know that in autotransformer there is both conductive power and inductive power, whereas in two winding transformer there is only inductive power. Therefore, if two winding transformer is reconfigured as autotransformer, then kVA rating of autotransformer will be greater than kVA rating of two winding transformer. And in numerical problem, if it is given that a two winding transformer is configured as autotransformer and it is asked to find the inductive power of autotransformer, then there is no necessity of calculating the inductive power by using this relation, because the two winding transformer rating itself is the inductive power. That is, if single phase transformer is reconfigured as autotransformer, then inductive power is the rating of single phase transformer itself. There is no necessity to calculate inductive power by using this relation. And as kVA rating of autotransformer is greater than the kVA rating of two winding transformer, use this relation, so which can be equated to 1 by 1 minus k. So kVA rating of autotransformer by the kVA rating of two winding transformer can be equated to 1 by 1 minus k. And one important point that you must make an important note, that in comparison with single phase transformer, the same requirement can be met by autotransformer with less copper material. Therefore, the ratio of weight of copper of autotransformer to the weight of copper of two winding transformer can be equated to 1 minus k, because weight of copper is less when compared with the two winding transformer. So you can relate this with 1 minus k, and this relation can be obtained like this. And it is known that weight of copper is directly proportional to length and area of cross section, and length is directly proportional to number of turns and area of cross section is proportional to current. So weight of copper is directly proportional to number of turns and current. And in case of two winding transformer, the number of primary turns are N1 and the current flowing through that turns is I1, and the number of turns of secondary winding of two winding transformer are N2 and the current flowing through that winding is I2. Therefore, weight of copper of two winding transformer can be taken as equal to N1 into I1 plus N2 into I2. And coming to the case of autotransformer, the weight of the copper in autotransformer can be equated to the number of turns present between the point A and C and the current flowing in through that turns, plus the number of turns present between C and B and the current flowing through that turns. Therefore, weight of copper of autotransformer can be taken as equal to number of turns present between A and C is Np minus Ns, and the current flowing through that winding is IH, plus the number of turns present between C and B is Ns, and the current flowing through that winding is IC. And here Np means N1 and Ns is N2 and IH means the primary current. So let us take it as I1, and Ns is the secondary number of turns means N2, and IC is the current flowing through the common winding, which is equal to IL minus IH, and IL is the secondary current, so I2 minus, and IH is primary current, so I1. So that is equal to N1 I1 plus N2 I2 minus 2 N2 I1. Therefore, divide weight of copper of autotransformer to the weight of copper of two winding transformer. So that is equal to N1 I1 plus N2 I2 minus 2 N2 I1 divided by N1 I1 plus N2 I2. So this by this will give you 1 minus 2 N2 I1 by N1 I1 plus N2 I2. So that is equal to 1 minus, take this N2 I1 to the denominator, so 2 by N1 I1 by N2 I1, which will give you N1 by N2 plus and N2 I2 by N2 I1, which will give you I2 by I1. And from this case, N1 by N2, that is NL by NH we defined as K, so which is equal to N2 by N1. So N2 by N1 is K here. Therefore, N1 by N2 represents 1 by K. And similarly, I2 by I1 means here IH by IL, which is I1 by I2. So I1 by I2 is K, means here I2 by I1 is 1 by K, and 1 by K plus 1 by K is 2 by K, and 2 by K is K. So that implies weight of copper of autotransformer to the weight of copper of two winding transformer is equal to 1 minus K. This is one more important relation. That implies weight of copper of autotransformer is equal to 1 minus K into weight of copper of two winding transformer. So weight of copper of two winding minus K into weight of copper of two winding transformer. So which implies when weight of copper of autotransformer is compared with the weight of copper of two winding transformer, so this is the saving in copper. So therefore saving in copper of autotransformer is equal to K times weight of copper of two winding transformer. Therefore from this relation you can note that saving in copper is more when K approaches unity, because we defined K is less than 1. So saving in copper in autotransformer will be more when K approaches unity. And in comparison with single phase transformer, using autotransformer is advantageous when K is greater than 33.3 percentage. That is, if K is greater than 0.333, then autotransformer is preferred to single phase transformer. Therefore, based on the weight of copper, we can derive few more important relations, that is about losses. So per unit losses of autotransformer to the per unit losses of two winding transformer. As the copper material used in the autotransformer is less when compared with single phase transformer, so the copper loss in autotransformer are less when compared with two winding transformer. Therefore, per unit losses of autotransformer will be less when compared with the per unit losses of two winding transformer. So we can equate this relation with 1 minus K, because 1 minus K is less than 1. And similarly, per unit impedance of autotransformer to the per unit impedance of two winding transformer. As the copper winding used in autotransformer is less when compared with two winding transformer, means the impedance is less when compared with single phase transformer. Therefore, per unit impedance of autotransformer is less than per unit impedance of two winding transformer. So you can equate this relation with 1 minus K. And next, voltage regulation. So percentage regulation of autotransformer to the percentage regulation of two winding transformer. And in case of autotransformer, as single winding is used, means the leakage reactance is less when compared with two winding transformer, because there two windings are used. Here only single winding is used, and in this case the leakage flux is low. If leakage flux is low, means leakage reactance is low, which means leakage reactance drop is low, means voltage drop is low. And if voltage drop is low, which implies regulation is low. That is what we require. Therefore, percentage regulation of autotransformer is less when compared with percentage regulation of two winding transformer, and that we can equate to 1 minus K. And next, short circuit current of autotransformer to the short circuit current of two winding transformer. And we know that short circuit current is equal to short circuit voltage by impedance. And in case of autotransformer, we decided that impedance is less when compared with the impedance of two winding transformer. Therefore, in autotransformer, as impedance is less, short circuit current is high. Therefore, short circuit current in autotransformer is high when compared with the short circuit current of two winding transformer. Therefore, here we must equate this relation with 1 by 1 minus k, because 1 by 1 minus k is greater than 1. So, by taking k is equal to VL by VH, we got k is less than 1, and because of that, it makes us simple to recall all these relations. Therefore, the following are the advantages of autotransformer over single phase transformer. Copper saving is more, and the saving of copper is k times the weight of copper of two winding transformer. And the second advantage of autotransformer is voltage regulation is less than voltage regulation of two winding transformer. And the other advantage is efficiency of autotransformer is greater than the efficiency of two winding transformer. And as copper saving is high in case of autotransformer, so size is reduced and obviously cost is reduced. Next, disadvantages. And if this is the autotransformer and let this be the load, then loads are designed to operate at a particular voltage. If suppose all of a sudden high voltage is applied across the load, then what happens? Load will get damaged. And this is what happens in autotransformer, because if all of a sudden due to some unknown reason this common winding gets open circuited, then what happens? This entire high voltage will be applied across the load, and because of which load will get damaged. So this is the main drawback in autotransformer. And the second drawback is high short circuit current. These are the main advantages and drawbacks of autotransformer. A single phase two winding transformer can be reconfigured into autotransformer. Now let's see how to do it. And to understand how to reconfigure, let's discuss a simple concept. That is, we know that if this is the one voltage source and let this be the another voltage source which is connected in series, and let's suppose this is V, and if you connect a voltmeter like this, then the voltmeter will read 2V. And if suppose this is the one voltage source and the other voltage source is connected like this, and if you connect a voltmeter across this, then the voltmeter reading will be 0. That is, this is in additive mode and this is in subtractive mode. And the same concept you can apply to this single phase transformer for reconfiguring it into an auto transformer. That is, to reconfigure it into a step up auto transformer, use this concept, and to reconfigure it into a step down auto transformer, use this concept. That is, in place of plus, let's consider dot, and this is non-dot end, this is dot end, and this is non-dot end. So to get additive mode, what we must do? We must connect dot end to the non-dot end and non-dot end to the dot end. And the same concept we are applying here to get step up auto transformer. So this is the element, means this is the element, and to this element this is the dot end, so this is the dot end, and this is the non-dot end, so this is non-dot end. And what we must do? We must connect non-dot end to the dot end. So non-dot end is this, and this is what we are connecting it to the dot end, and the output is being taken from the dot end to the non-dot end. So output is taken like this, dot end and non-dot end. This is voltage, and if you rearrange this, this is how it will look, and this is step up Autotransformer. Till now we have seen the case of step down autotransformers, and this is the case of step up autotransformer. And now to get the step down autotransformer, what we must do, we must connect non-dot end to the non-dot end, that is simply non-dot end to the dot end, and simply take the output like this. And if you reconfigure this, this will look like this. This is dot end, and this is which is connected to the non-dot end. So this is what, and input is applied across this and output is taken like this. So this will give you the configuration of step down autotransformer. And simply to remember this, if voltmeter is connected across the dot ends, okay, this is dot end and this is dot end, or if voltmeter is connected across the non-dot ends, then that transformer will act as step down autotransformer. And if the voltmeter is connected across the dot end and non-dot end, that will comes under step up autotransformer. And following are the points that you must remember before solving the numericals. The first point is current flowing in two winding transformer remains same after reconfiguring into autotransformer. That is, if suppose this is the two winding transformer and let the primary current be I1 and let the secondary current be I2, and if this is reconfigured to autotransformer like this, then the current flowing in primary winding is I1 and the current flowing through secondary winding is I2. That is, after reconfiguring, the currents in the windings will not change. And the second point is, as the two winding transformer is configured into autotransformer, means here the losses in the transformer doesn't change. So total losses of two winding transformer remains same after reconfiguring to autotransformer. That is, total loss of two winding transformer is equal to the total loss of autotransformer. And the third point is, if the dot ends are not given, then the current flow direction in common winding of step down autotransformer is bottom to top, and in case of step up transformer, the current direction in common winding is top to bottom. And fourth point, if you want to find inductive power, simply there is no need to calculate the inductive power. Inductive power is the rating of two winding transformer itself. So these are the four important points that you must keep in mind before solving the numericals.